All right, 10 seconds. Okay.
Okay, so welcome to the Phobos and Deimos, the Moons of Mars course in Science and Exploration of Phobos and Deimos. And today we're going to have a really important lecture by Andy Rivkin entitled Ambiguity of Compositional Data for Phobos and Deimos. And my name is Jim Head, Planetary Geoscience at Brown University, and I'm going to be the person who handles all the questions. And so what we'll do today is, first of all, we'll take questions in the chat box, and I'll try to integrate those, and then I'll lead the discussion at the end and pose a synthesis of the questions to Andy as we go along. So first, I want to point out that the course is sponsored by Solar System Exploration Research Virtual Institute, SERVI. You can see the logo in the middle there, and of course also by co-sponsored and co-organized by the SEED, MIT, Brown University, SERVI Evolution and Environmental Exploration Destinations, and the UCF, University of Central Florida, Center for Lunar and Asteroid Surface Science. So today's speaker is Dr. Andrew Rivkin. Andy got his PhD in planetary astronomy from the University of Arizona in 1997. And he's a member of the Planetary Exploration Group at Johns Hopkins University Applied Physics Lab. And Andy has really been focused on, in his career, near-infrared spectroscopy and spectrophotometry of asteroids, and particularly looking at things that have a high incidence or possibility of water and organic materials. And he's done a lot of range of work from looking at asteroids such as 1996 FG3, NEO that has clay minerals, to 24 Themis, an outer belt asteroid in which he and his team found water ice. So Andy's also taken a look at extensively at Ceres, and so perhaps we can get him to give another talk on that at a future time, in a future seminar. And today he's going to talk to us indeed about the ambiguity of compositional data for Phobos and Deimos. Andy?
All right, thank you, Jim. And thanks to the SEED and class SERVI teams for having me give this lecture. I'd also like to, I guess, thank the SERVI Central. I don't know if I do this. Okay, right. So does that go to my slides? Nope. All right, well, I'll wait for someone to slap my slides up, but I'm going to talk today as...
We could go straight to the slide.
Sure.
We can go straight.
And I'd like to thank everyone. I know today's a holiday. I don't know how many people celebrate Canadian Thanksgiving, but I appreciate you guys taking the time on this important holiday to see this talk. So I changed the title slightly because talking about ambiguity is kind of puts a negative spin on things. Instead, maybe just to say how there are subtle features in the spectra of Phobos and Deimos, and that's what we're going to talk about, as well as why it's kind of, and how it's taken us a while to recognize that those are there. Whoops, that's not the button, that's the button. So I'm going to start with some motivation, talk a little bit about spectroscopy basics, just a little bit to get everyone at least sort of over the same place. More specifically about small bodies, since Phobos and Deimos are often thought of in the context of asteroids and other small bodies, the challenges that we're faced when we try to understand the composition of Phobos and Deimos, and then kind of a narrative of where we've been with the data that we have, and then finish up with where we might be going with this. So in particular, I'd like to thank Scott Murchie and Rachel Klima. Scott provided some of the slides that I'll be showing today. Rachel is in Boulder. She's not going to be speaking today, but hopefully she'll be available in the chat box as necessary to help me out if I need it. And also, Abby Freeman is is all over the second half of this talk. She's done a lot of the most recent work. She's now at JPL. I thought I saw her that maybe she had dialed in. So Abby in particular should get a shout out there. So in terms of motivation, Phobos and Deimos are important because along with the moon, they are the only known natural satellites of the terrestrial planets. The gas giants have dozens to, well over 100 among the four of them, and among the four terrestrial planets, there's only these three. And as we know, Phobos and Deimos are very different from the moon. The Earth only has the one large satellite. Phobos and Deimos are both small satellites. So we want to know, why are they different, and what does that tell us about the way the planets evolved and the early times in the solar system? Why don't Venus and Mercury have satellites at all? And then abstracting another level or two, what does that tell us about the search for Earth-like planets, for Earth-mass planets, for habitability outside the solar system? What does having a moon, or a moon more like ours, or a moon's more like Phobos and Deimos, do for a planet, so to speak? There are leading theories for how Phobos and Deimos formed. I think some of the people listening in are in the process of helping to shape those. But it's still really not well understood how Phobos and Deimos formed. I know you're going to get some lectures on this in coming weeks, specifically about the formation, but as maybe a tease, not a spoiler, the two main theories, or groups of theories, either suppose that Phobos and Deimos formed where they are now, from Mars or very close to Mars, or else they formed farther out in the solar system among the asteroids or among the KVOs. And each of those formation locations has different implications for the following history. If Phobos and Deimos are pieces of Mars or pieces of proto-Mars, then we could really learn a lot about early Martian history by visiting Phobos and Deimos, and they may have material that's gone from Mars itself, preserved in orbit. And it would be certainly a very easy Mars sample return, which I don't know if the Mars community would really want to hear, but that's certainly the case. If Phobos and Deimos are instead asteroidal in origin, or even from further out in the solar system, then that has implications about the delivery of outer solar system material, including a lot of ice, a lot of prebiotic material to the terrestrial planets, not just Mars, but Earth and, again, Venus and Mercury. And it also would provide potentially an easy way to get a lot of cometary or KVO material, again, in the same way that if they were from Mars, they could be a Mars sample return proxy. Finally, because this is sponsored by Survey, which has both science and exploration aspects, Phobos and Deimos have been looked at as possible bases for human exploration of Mars, either as a first stop on the way down to the surface of Mars, or as a place where rovers or other telerobotic assets can be used. So understanding what Phobos and Deimos are made of will help us understand how they are best used as bases for Mars exploration. Okay, so the composition is really the key to figuring out the origins of these moons. I'm not going to talk through everything on this slide. This came from a paper of Scott Murchie's that I think is in the reading list. But again, basically, we're looking at two broad classes of origin stories for Phobos and Deimos. Either they're formed from Mars material, or they're more primitive material from further out in the solar system. And each of these origin hypotheses, as you break them down into more specific pieces, come out with a predicted composition and with predicted elemental abundances and predicted mineral abundances. As I talked about briefly near the very end, to get elemental abundances, you really need to go to these objects and measure measure them in a way that they have not been measured yet. But for minerals, we have a pretty good way of determining mineral compositions of things. That's via spectroscopy. So just a few slides on spectroscopy. Basically, you shine light either on or through a material and see how much light is left when you're done with that. So for gases, it's very easy. Molecules and atoms are relatively simple systems, and if any of you have had quantum or had a lot of quantum, you know that this is intimately tied to that. Light comes in and takes out, and an atom or a molecule will remove light of a particular wavelength, and only that wavelength. So observing something like a planetary atmosphere or a cometary coma is relatively straightforward. If you want to look at a solid surface like the moon or Mars or Phobos and Deimos, it is somewhat more difficult. Solid surfaces are composed of mineral grains. The mineral grains are of different sizes, maybe a whole mixture of different sizes. The crystal structures can be different. There are impurities. You can have compositions of minerals like olivine that have slightly different amounts of iron or slightly different amounts of magnesium, or again, minor elements. The angle at which you observe a solid surface can change the spectrum. So they are not as clean as an observation of a spectrum of a gas. So here on the right, let's see if I remember how to call up. Nope. How to call up? There it is. All right. So this is on the x-axis is wavelength in nanometers. We'll be using either nanometers or microns today, where 1,000 nanometers is 1 micron. And then reflectance on the x-axis, that's not the x-axis, reflectance on the y-axis, which is just a fraction of light that's reflected off of a surface. And different important rock-forming minerals have different spectra. So this pyroxene has a lower reflectance near 1 and 2 microns, while olivine has more like a one single absorption near 1 micron. Some important rock-forming minerals don't really have any absorptions at all. So you see a lot of straight lines, some with higher reflectance and some with lower reflectance. So it's a bit more of a challenge, but particularly if you have a surface that is of the right kind of stuff, you can still make mineral identifications. This plot here is from a paper of Rivkin's from 2001, where we observed the asteroid 1999 SF36, which is better known today as Itokawa. It's been renamed. It was the target of the Hayabusa mission in the early years of this century. And by observing the spectrum and deconvolving its spectrum into several Gaussian components, it was determined that it was most like happily, when pieces of Itokawa were returned to Earth, we did in fact find that this was the right, an accurate measurement of its surface. It looks like an allochondrite. It is an allochondrite. So what do we get when we look at Phobos and Deimos? Phobos and Deimos were first suggested to be asteroids 45 years ago by Brad Smith based on Mariner 7 data. So this is the frame that he used, and even back then, Phobos and Deimos were kind of underdogs. They've maintained this underdog status in a lot of ways. So this is Phobos seen against the surface of Mars, and this is the first measurement of Phobos its size could be calculated. We knew how bright it was, and so it was seen to have a low albedo, a low reflectance, to be a dark object. And this low albedo was something of a surprise. It was recognized, as I'll show in the next slide, that it was a strong constraint on composition. Just a point of how Phobos and Deimos have kind of been not as well observed as you might think, given how close to Mars they are. This is from Pollock et al. 1972, and in the box there on the left, you can see that basically the only reason that Mariner 9 observed Phobos and Deimos at all was that there was a Martian dust storm. They didn't want to bother looking at Mars. They figured they might as well do something since they had a spacecraft there. They looked at Phobos. But then, to the point I just made, it was recognized again 40-something years ago that the low albedo is diagnostic of composition, and the only two materials that were likely to be out there that had this low albedo are basalt and carbonaceous chondrites. Indeed, it was immediately realized that the history is going to be very different depending on if they are basalt or if they are carbonaceous chondrites. So we've spent the last 40 years plus trying to determine really which of these is more likely. Through the 70s, there was some spacecraft data. There was that image from Mariner 7 I showed. There was a little bit from Mariner 9. The Viking orbiters were really the first to really give us a good sense of what Phobos and Deimos looked like. This is a Viking image of Phobos on the right. But it was also the time when spectral data for asteroids and meteorites were really first getting to be available. There was no library of spectra to compare Phobos and Deimos to, so everything kind of had to progress together. So asteroid data started to get taken. This is not real data on the right, although it is, I guess, from the right period, that kind of late 70s, early 80s. So asteroids are divided into spectral classes based on their visible data, and then typically we compare those spectra to lab spectra. For simplicity, and you can put simplicity in quotes if you like, the spectra get binned together and classified, and we talk about a particular asteroid class or another. These classifications use letters. We have most of the letters of the Latin alphabet is used. Some two-letter combinations are used. And these letters are grouped together. Again, this is kind of evolved over 30 plus years. We see a variety of rock-forming minerals in the asteroids, and these are again associated with particular classes. So the S complex here, this has absorption bands near 1 and 2 microns. These are due to olivine and pyroxene. They're associated with igneous minerals, but also the ordinary chondrite meteorites, which are primitive, which are undifferentiated. This is the class that includes asteroids like Eros, and many, if not most, of the near-Earth objects are in this particular class. The C complex includes asteroids like Ceres. These are low albedo. These are associated with the carbonaceous chondrites. This is the group that Phobos and Deimos were first thought to fall in. And then these other classes, X includes a range of material, and it's basically defined by not having any absorption bands, which is something of a problem, but again, that's what we're talking about here. And just for completeness, I'll point out the V class here with these deep absorption bands due to olivine, due to pyroxene. Everyone's calling me. No one should call me. I'm sorry. The V class is Vesta, which is a large asteroid in the main asteroid belt. This shows again, these asteroid classes from the previous slide with actual reflectance put in. So the V class here is high reflectance, and the C class is lower reflectance, with the D class lower reflectance yet. When we look at the distribution of asteroids in the asteroid belt, we see that the different classes fall in different places. So there's not a mixture of these classes throughout the belt willy-nilly. Back in the 80s, this was recognized, and it was thought that the asteroids in the inner part of the belt were more igneous and more processed. Ones in the outer belt were more primitive and water rich. These exact labels are not necessarily thought to be the case anymore, but the pattern overall is still the same. This plot is from a much more recent paper and divides up not only by distance in the asteroid belt from inner, middle, outer, and further, but also by size, with the largest group to smaller asteroid sizes as you go down in the plot. And you can see even if you can't quite read the individual letters, the fraction of each class changes as you go further out of the belt. This is why, if we can associate a composition or an asteroid class with Phobos and Deimos, that gives us at least a chance to work backwards and determine where they might be from, if they are asteroidal. Most asteroid work is done in the visible and near IR. There is some work that's done beyond it. I don't know why that didn't come out so well. That's too bad. If you go beyond 2.5 microns, you start to get absorptions that are due not to silicate minerals, but instead due to OH, CH, and other volatile type material like ammonia. These data are more difficult to obtain. And in fact, this gap here in the data is due to the Earth's atmosphere, where water in the Earth's atmosphere basically means that nothing comes through the atmosphere. You can't see it. If you go to longer wavelengths yet, you find the mid-IR contains information about SiO and bonds, so more of a silicate, again, measurements. So the earliest Earth-based observations, this again is from last century. Given that most of the spacecraft around Mars only were focused on Mars and sent back relatively little data for Phobos and Deimos, we were left piecing together what we could from those spacecraft along with Earth-based observations. This map here by Phil Stuck was based on Viking data, but is something that we used to use at the telescope to see which part of Phobos we were looking at. And part of the problem is that Mars really dominates the area. So this is to scale. This is, I think, taken from Wikipedia, naturally. And the two arrows show the positions of Phobos and Deimos, which are, you can just maybe make out Phobos there. I can't see Deimos. And Mars simply dominates the scene. So that proximity to Mars means that observations from the ground are very difficult. There's scattered light from Mars that has to be dealt with. Phobos is so close to Mars that even if you can deal with the scattered light, there's a large fraction of time when it's either in front of or behind Mars and not observable. The HST did observe Phobos on occasion, but Spitzer has been unable to observe them because Mars is too bright. There's an avoidance zone. I don't know if JWST will be able to observe Phobos and Deimos or not. I think it's unlikely. Again, similarly, Mars is just too bright, and it would be very, very challenging for those telescopes. And then on top of that, Deimos independently is a bit fainter, sufficiently faint that some measurements would be hard even if Mars weren't there. Phobos is bright enough that if Mars weren't there, it would be an easy target. So the first spectra of Phobos and Deimos came from the Phobos 2 mission, the Soviet Phobos 2 mission in the late 80s. And prior to that, there was a little bit of spectral data available from Viking, which suggested that along with the low albedo, there was a flat spectrum. The Phobos 2 data showed instead that at least part of Phobos was very, very red, had a very strong spectral slope with increased reflectance with increasing wavelength. They also found evidence for a less red unit. We call it the bluer unit, but really it's just less red, associated with the Stickney crater. And this information for Phobos is also agrees with what we had for Deimos from the ground. Will Grundy was able to get a visible spectrum, and some folks went to the RTF, me and Jim Bell and Dave Trilling in the late 90s, and got some Phobos and Deimos data. And so this is our plot here on the right. And you can see that this is a very red-sloped spectrum. I'll have some comparisons in another slide or two. But the open symbols are this red unit from Phobos 2. These black points are our Deimos data. I guess the triangles, so the open triangles down here are also Deimos. Those agree well with that red unit of Phobos. The red unit that we measured from the ground also agrees well, and so our blue unit is not as red. But there are no strong absorptions at any wavelength. And if you think back a few slides when I was talking about Itokawa, the success of comparing Itokawa to the meteorites was based on matching and deconvolving spectral features, and there really are none in these spectra. So that's a bit of makes things a little more difficult. The low albedo was independently confirmed, not just from measuring the size and brightness. We also could measure thermal flux from Phobos and Deimos at these wavelengths. And while later measurements will give us much better spectra, again, the overall story stays pretty much the same. So we have featureless spectra. So how do you handle that? I've been reading some Sherlock Holmes, and when you've eliminated the impossible, whatever's left has to be the truth. So there's no obvious pyroxene, there's no obvious olivine, there's no obvious much of anything, no strong absorptions due to hydrated minerals. They don't look like inner belt asteroids. They don't look like igneous rocks. They don't look like Mars. So we have to look to bodies that have similar spectra and known compositions and try to work back from there. So as a small bodies person, the first thing you do is you think, well, maybe it's a small body. There are a set of captured asteroids and captured comets that are circling the gas giants. Most of the non-Galilean satellites of Jupiter are probably captured bodies. Those also tend to have very red spectra and very low albedos. And in fact, that type of spectrum with a red slope and a low albedo is associated in general with primitive outer belt or outer solar system bodies, whether that's the Trojan asteroids, which co-orbit orbit the sun at the distance of Jupiter, whether it's cometary nuclei, whether it's very red, ultra-red KBOs. So that's shown here on the right, where Phobos and Deimos are in the thicker lines. The thick red one is the Phobos red unit. The thick blue one is the Phobos blue unit. And those fall among these Trojan asteroids, D-type asteroids, comet sighting spring. And they really don't look like these S-type asteroids or the C-type asteroids that are associated with the carbonaceous chondrites. So this is an exciting possibility. It's not obviously crazy to say other planets have captured KBOs as satellites. Maybe Mars captured Phobos and Deimos as well. If they did capture, if Phobos and Deimos are captured from the outer belt or the outer solar system, that would also suggest that they might be volatile rich and organic rich. And again, that would be something that would be very exciting for people who want to make Phobos and Deimos into the initial bases for human exploration of Mars, because that would mean that water would be potentially plentiful and potentially something that they could get at very easily. However, there's more than one way to be red and featureless. On the right here is a plot from Sarah Noble's work, where she was looking at the lunar surface and looking at how soils change when they're exposed to space. They're exposed to micrometeorites, they're exposed to the solar wind, they're exposed to the UV, and that leaches, probably not leaches, but someone else might have a better word. It takes the iron out of the silicates and deposits it on the surface as nanophase iron, as it's called. And that process, as shown on the right here, can take a material that is relatively high albedo and reflective, and makes it into something that's lower albedo and red sloped. So the spectra seen on Phobos and Deimos at least are qualitatively consistent with mature space-weathered lunar soils. The albedo overall doesn't quite match. Phobos and Deimos are more like 5 or 6% albedo, and these space-weathered lunar soils are more like 10 or 15%. But I don't know that anyone has looked at what a Martian basalt would look like if you space-weathered a Martian basalt instead of a lunar basalt. So that possibility is at least still out there. If we are looking at space-weathered silicates, space-weathered basalts, then instead of a volatile-rich, organic-rich captured body, you're looking at a big piece of dry rock, which is not as easy probably to make a base out of, but that's it is what it is, if that's what it is. In this case, given the way that the maturity works, it suggests that maybe the blue unit and the red unit on Phobos have the same composition, and they're just slightly different freshnesses. The red one has been altered more or has been exposed longer and so has gotten more mature. And the blue unit perhaps has not been exposed as long, is younger, and is not as mature. Oh, and I should have shown this. So this explicitly compares the Phobos red unit in the symbols here and the Phobos blue unit in these symbols to two Highlands materials. These are, I did see there was a question, I should have said this anyway, these are all scaled to 1, normalized to 1 at 0.55 microns. So these have the albedo taken out of them. So, can we do better? The answer is yes, we can do better. We have spacecraft around Mars all the time now, and all they do is look to serve us, I guess. So both MRO and Mars Express have measured Phobos and taken pictures of Phobos, taken spectra at Phobos, and MRO has also observed Deimos. And on the right here are, in fact, high-rise images of Phobos and Deimos. The amount of data is relatively limited because these are designed to look at Mars and not designed to look at Phobos and Deimos. We're happy for whatever we get. At least in terms of CRISM, there were 3 CRISM images of Deimos, 3 CRISM images of Phobos. You can see the resolutions there, about 1 kilometer per pixel for Deimos and 350 meters per pixel for Phobos. The observations were made over the night side of Mars to try to avoid any complications from Mars shine. And there are also corrections made for photometric effects. When we observe from Earth, these are just point sources. When we have spacecraft observing, they're obviously going to have different phase angles depending on which part of the satellite you're looking at. And it says so right here, but again, this is much of this next sections all comes from the work of Abby Freeman at JPL, who's published several papers in the last few years. And we finally get some kind of clue, finally get some kind of absorption band. And we have 2 that now we can talk about. The first one is centered at about 0.65 microns. It turns out that we actually did observe it from Kitt Peak several years before, but we never quite believed it, in part because of the difficulties of observing Phobos. But this is a telescopic spectrum, and observations of the red unit on Phobos and of Deimos show this absorption, and it does not show up in the blue unit, either from the telescope or from the spacecraft. If we take out if you take out the slope and take out the continuum, again, you can see here the blue unit, there's not much of anything. In the red unit, both from the telescope and from the spacecraft, here's something. So that's great. We have a band. Where do we see this band? It is consistent. I'm going to skip this one. Consistent with phyllosilicates. So these are all clay minerals, and phyllosilicates are seen in carbonaceous chondrites when they are seen with absorption bands at about this wavelength. It's attributed to saponite group phyllosilicates. And here, indeed, for a heated nontronite, you get a pretty decent match with the band center for Phobos. However, you also can get that band center if you, instead of modeling it as a mineral, if you model a mixture of micron and submicron iron grains, you can also get something at about the right place. And unfortunately, these were, again, kind of the 2 possibilities we had just been talking about. If it was a captured outer belt type body, you might expect some kind of clay mineral. If it's a space weathered silicate, you might expect nanophase iron. We also, Abby et al. Also found OH on the surface of Phobos and Deimos. This was a first. It's been expected since the 70s, and it's this band right here, this dip, at about 2.8 microns. So again, it's consistent with carbonaceous chondrite, primitive composition. Those objects have those meteorites have OH in their minerals, so that's what you'd expect. But the story is again never quite as tidy as you'd like, because if we had found the OH in the 70s, we would have said case closed. This is what it is. But in the intervening years, OH has been detected on the surface of the moon, our moon, the Earth's moon, shown here in the paper by Jessica Sunshine et al., who where Deep Impact found OH. Cassini found OH on the surface of the moon, and of course M cubed on the Chandrayaan-1 satellite found OH. So, at least on the moon, it's at least some of the OH is considered to be consistent with solar wind and planet hydrogen. So, if it's happening on the moon, Phobos and Deimos are only a little further away. There's no Martian magnetic field, certainly not a strong Martian magnetic field to protect their surfaces from the solar wind. So, this also doesn't help as much as we would have liked. If you look at the distribution of these two absorption bands across Phobos, just for completeness here, you can see that where these are the two units are defined by their visible and near IR ratio. The blue unit stands out really well here, and it's a good match to where there is not a 0.6 micron band and where there is really not a OH band. And instead, the places with the deepest OH band is the red unit. And this is also true on Deimos. I'll talk about the mid-IR data just a little bit. This has been less well studied in general. There have been some mid-IR observations on site by Mars Global Surveyor and Mars Express, published in Girona et al. So what we see here in this top figure is the radiance, which is dominated by the black body flux of Phobos being at a temperature or several temperatures, depending on where you look. If you model that temperature and you divide out your fit, you end up with this mid-IR spectrum, which you can then compare to lab spectra. So Girona et al. Argued that what they see is consistent with phyllosilicates, and another area of Phobos is consistent with feldspar. They argued that the blue unit is the one that's consistent with phyllosilicates, which is the exact opposite of the results from the visible and near IR. However, and I see that Abby's on, which is good, Abby Freeman et al. Concluded instead that the footprint that they looked at was not the blue unit for the phyllosilicates, but was for the red unit, so that is consistent. There's no mid-IR observations of Deimos from within the Mars system, but there is one spectrum that's been published by Lynch et al. That's this bottom one. And they did not take the step of dividing out the black body, but if we zoom on in, you might see that you have an emissivity maximum there at about 8.5 microns. Maybe we're doing real-time science here. So if you like that, and you back up 2 slides, and you say, what does a maximum at 8.5 microns get you? You see that you are, again, consistent with phyllosilicates. So in principle, this all still hangs together. So as we start to hit the home stretch here, the question of what the relationship between the blue and red units on Phobos is probably one of the few, again, one of the few entries we have, one of the few levers we have into figuring out composition. And this plot here, this cartoon here on the right is from a recent paper of Vasilevsky's. I think he speaks next week, so I don't, again, want to give away too much. But you can imagine there are 3 general possibilities for the relationship between the blue and the red units. Either they're the same composition, but have different maturities. So one is a space-weathered version of the other. They could be different compositions, but come from the same parent body. Or they could have different compositions and come from different parent bodies. So, for instance, Phobos and Deimos needn't have the same composition if you think that the red unit on Phobos is Deimos dust. So I'll back up here. Even though you have 3 possibilities on the left, you have 2 possibilities on the right. 1 and 3 could look like case 1, and number 2 here would be number 2. This is represents the Stickney impact and various ejecta blankets from various impacts into Stickney and nearby. So the implications of these different possible relationships, if you really are looking at this case where you have an immature or an unexposed interior and an exposed mature exterior, the implication would be that Deimos also has a blue unit if you dig down deep enough, but we just don't see it. And for science purposes, one site is potentially sufficient to sample to understand either Phobos or Deimos. You just need to have the ability to get down deep enough to the immature material. If you have different compositions but the same parent body, like in case 2 here, then you would need multiple sites to understand the history of Phobos and the composition of the moons. You would need to land both here and here. It would also suggest that compositional heterogeneity is important on sort of kilometer scales in small bodies, which is something that we don't know right now, and that would be an important result. If we have different compositions and different parent bodies, so if we're up here and this is what Phobos really looks like, and you've got a bunch of Deimos on top of it, then again, they didn't have the same history. It also suggests that material exchange is maybe important between Deimos and Phobos. I'll also say that there's at least one more elephant in the room that I'm going to mention and then forget again because we don't want to deal with it, which is that we talk about the red unit and the blue unit, because Occam's razor suggests you make things as simple as things should be as simple as work. But Murphy's Law and many of these other slides show that you can have lots of ways of having a featureless material. So there might be more than one composition to the red unit. There might be 2 red units or 10 red units with slightly different compositions that are different in important ways. Again, I don't want to give away too much, but at least the Vasilevsky paper, which I think is also in your reading, suggests that if you look at the geology and do the photogeology, that this is actually the preferred case, and that this doesn't work when you look at the specifics of the ejecta blankets. I wouldn't say it's a slam dunk, if only because I'm an astronomer and not a geologist, but that's something you can ask Vasilevsky when he gives his talk. Okay, so where are we? Where do we go after 48 minutes of a rambling talk here? There are still, after 40 plus years, two compositional hypotheses for Phobos and Deimos that are still alive. The one that perhaps we can say is leading is that Deimos and the Phobos red unit are desiccated phyllosilicates. So that fits the visible and near IR data. It fits the mid IR data, and it's not it's maybe not preferred by dynamicists, but at least just in a compositional sense, this seems to fit the data. The Phobos blue unit, we still don't have any real insight into any direct insights into the composition. It's defined only by its albedo and a spectral slope. We still haven't found any absorption bands other than, I guess, the OH band in that blue unit. And we would expect hydrated minerals to be throughout these bodies. We expect them to be made of the desiccated phyllosilicates, and if you keep digging, you're going to keep finding more of them. We cannot formally rule out, I think, that the Deimos and the Phobos red unit is space-weathered material. In a formal sense, the nanophase iron does fit the spectra in the visible and the near IR. One could argue that OH is created by the solar wind. The mid-IR data is perhaps of low enough spatial resolution that's not as diagnostic as it could be. In this case, we also don't know what the Phobos blue unit is made of. And in this case, if the OH is created by the solar wind, then we would only expect to find it at or near the surface. So we need to move beyond what we've done to get much further. As one of the ragtag group of astronomers, we really done amazing stuff. The astronomers and the geologists. It sounds like I'm tooting my own horn. The other astronomers and geologists have really done amazing stuff using a very, very limited data set. But we definitely need more dedicated spacecraft campaigns to really get at what Phobos and Deimos are all about. Whether that means landers, geochemical data, I think that's the kind of step that we need to take. We might have. I'm always reluctant to say that something's at its end, but it's difficult to see how much more we can get out of orbital or flyby techniques. Maybe moving further into the mid IR or something like that. So I think that having a lander that can get some geochemical data, having some gamma ray, X-ray data, something like that is really going to be necessary. And of course, we are awaiting sample return. The Russians have tried a few times. My understanding is that that's in their medium-term plans to try again to do a sample return. I understand there are some Japanese plans that are being considered, or maybe they're further along than that. So hopefully, like I said, it's been 40 years that we've slowly been groping our way forward. It's certainly my hope that in the next 20 years, we'll be able to, someone will be able to give this talk with this is what they are, this is where they come from, and this is what that means. And I believe that is my last slide. So it is much harder than I would have thought to give a talk in one's own office with no feedback from anyone. So hopefully Hopefully everyone's still there.
We're here, Andy. That's a really great summary, and I think we'd like you to be the one to give the talk in 10 or so years to actually tell us which the right answer is. Okay.
That's fine with me. It's fine with me.
So we have a number of questions. I think thanks to the people who have actually answered some of the questions that have come along. I think a critical question that might be kind of an overarching one is, for sample return, what in fact would you see as, how much sample would you need? How much, where would you try to take it? And would you need it from both bodies to actually be able to determine the origin of both Phobos and Deimos? Can you talk a bit about that?
Well, that's a great question. I could give the generic small bodies answer. I think the generic small bodies answer is that I think it was Derek Sears did some study 15 years ago-ish that suggested that 10 grams would be enough to be, this is for an asteroid, not for Phobos and Deimos specifically, would be enough to show, to be representative. You can, of course, determine composition from much, much, much less, but the concern would be that you have a representative piece. I think that whether you need to land on both, whether you need to sample both, I think you would need to sample Phobos first. And then, depending on if something like you get different grains with different oxygen isotopes suggesting different parent bodies, that might then drive you to have to go to Deimos to understand whether some of that is Deimos material or not. I'm under the impression, and your own work, you plural work on the call have shown the likely amount of Mars material that's going to be on Phobos. I don't think that you're too likely to get spoofed by that. I think if a Phobos sample return came back and found a lot of Mars material, that would itself be, that would be a slam dunk. It's hard answering
thanks.
questions, not seeing anyone too.
That's okay. We have more. So Catherine Elder pointed out that there's some spectral differences between space-weathered lunar soils and standby. People are typing madly here. And Phobos and Deimos, and how do they compare to other space-weathered airless bodies such as Itokawa, for example?
Yeah, so the asteroids, this one I might even have a relevant slide. So for asteroids like Itokawa, the most common NEOs are this Q type. So these are silicate bodies. These have olivine and pyroxene, and space weathering seems to take the Qs and make them into S's. So it makes the absorption bands a little bit less, and it gives you this red slope. So qualitatively, it does the same kind of thing that it does on the lunar soils. But it's space weathering is sensitive to the starting materials. I think we can be confident that Phobos and Deimos did not start out looking like this. Whether it started out looking like one of these other groups is TBD. And then, like I said, if it seems like someone could take a spectrum of a Mars basalt and computationally figure out what it would look like if it were space weathered. Whether it would be a diagnostic enough spectrum to say that it works or doesn't work, I don't know. But
okay, so I think Wesley Chambers asked, do you think the data at hand suggests a common origin or formation mechanism for Phobos and Deimos, or do you think we can actually have sufficient data to actually tell that at the present time?
strictly talking about the compositional data, and I know that dynamicists have definite opinions because of the way Phobos is evolving inward toward Mars, Deimos is evolving outward. So there are various dynamical constraints. I think that the similarity between Deimos and most of Phobos spectrally is just really very suggestive that they have a similar origin. Um, Again, at least from an Occam's razor point of view, it's the easiest thing to suggest. Nothing rules it out at this point, and it seems like otherwise you would. The argument otherwise would be that you've got enough Deimos material over Phobos to code it. That seems not proven.
Okay, a question from Michael I. He asked, can Maven help in terms of distinguishing origins, anything with space weathering or anything like that?
I don't know what Maven. I don't know Maven's payload well enough. I know they made a great effort in observing Comet Ison just after they arrived, but I don't know. I don't know what they could do with Phobos and Deimos.
Okay, if anybody has any thoughts on that, please put them in the chat box. Umberto Campins asked, what about the composition of the Stickney projectile? Any way data at hand, any of the color units, etc., might be related to that, or just to maybe the freshening associated with that?
Oh,
I guess the real question.
That would be tough. I think that even here on Earth with big craters, that can be difficult at times to figure that out. And that would be a question more for someone like Eric Aspog or someone who's done the impact modeling for Stickney to see how much of the projectile survives. I'm saying I don't know a lot. It's a humbling experience.
No,
Another humbling experience.
That's good. No, that's a good reference. Eric's work is very relevant there, I think. So let's see. Driss Takir says from Flagstaff that pointed out that using the sample return approach, one way to do that is, of course, to use a projectile to small carry-on impactor like Hayabusa 2, for example. So that's a good idea, and a number of proposals for sample return have actually utilized that. I think Aladdin and maybe some others have used that idea as well. Any additional comments on that?
Yeah, that's right. Aladdin was before I got to APL, but they were planning to do kind of a couple of drive-bys and sample dust from Phobos and Deimos. Actually, that's another issue that I don't know if anyone in this series is going to talk about. It's thought that because of the constant rain of impactors into Phobos and Deimos, that there's a dust torus that accompanies the two satellites in their orbits around Mars, but that dust has never been sampled. So whether that is, whether there's a way to use that dust, if found, to get some insight. I don't know. We had 3 great discovery proposals aimed at Phobos and Deimos in this last round. Unfortunately, none of them went forward, but hopefully some combination of them will be able to go forward and get at some of this data.
Okay, Rachel Klima got back to us here saying Maven is really designed for atmospheres. It's not really ideal for looking at solid surfaces, and she didn't know whether it has any chance of getting a UV signal off Phobos or Deimos, but would guess that the chances are quite slim. Thanks, Rachel. And Stephanie Eckert asked, what implications might the composition of have for a possible human mission to either Phobos and Deimos? You touched on that very early on, but maybe you could come back to that to say whether it's going to be a way station where you don't stay long, or something that's resources for a long stay and maybe a supply station?
Sure. Yeah. As you note, some people have both Phobos. I've heard both Phobos and Deimos touted as great spots for a human base, either again as a first stop or a place to telerobotically operate rovers on the ground. I've heard it touted as a place to kind of put the sample return cache um, that eventually would come back from Mars sample return. One of the key questions in human exploration is the resources and water and how much you have to recycle and how much material you can make on site. If Phobos and Deimos are captured asteroids, then they could have up to 10, 15, 20% water by weight. And that would be relatively easy to get. This is the kind of thing that some of the asteroid mining companies are trying to take advantage of with NEOs, is the idea of capturing water, mining water from primitive bodies. If Phobos and Deimos turn out to be like that, then they would be great spots for doing this in situ resource utilization. If they turn out to be big slabs of rock, they still would offer a lot of benefit, a lot of potential benefit in terms of not having to get up and down off of the Martian surface. You could still use them to robotically, telerobotically run rovers on the surface, but you would lose that in situ resource part, which is really appealing to a lot of the exploration community.
That raises another question, which Angela Kren points out, which is, do you think sample return is the only way to resolve the issue, or could further developments in spectroscopy or dynamical models provide the answer? So do we need the samples right away, or can we think of a technology that might actually help us tell, but also tell us where to go for samples better?
Yeah, I don't think that, I don't want to say sample return is the only way. There have been, and I don't want to come across too strongly, like I said, there have been, there were 3 discovery proposals that went in this last round. I'm certain that all of them had resolving this issue of the composition and the origin of Phobos and Deimos. I'm sure all 3 of them had them as very important questions. So all 3 of them came up with ways short of sample return to do it. Whether that means putting a lander down, something with an APXS, whether it means a gamma ray spectrometer that you use and a neutron spectrometer. I don't know that I don't know a lot about the mid-IR, but it seems like the mid-IR hasn't been fully used at Phobos and Deimos yet. So there's another possible remote sensing way. Sample return will be the most straightforward, but I do think there are other possible ways. And as kind of alluded somewhere, I think, this is strictly from the spectral, compositional, remote sensing point of view. We've been in a friendly battle with our colleagues who are dynamicists over various issues over the decades. It's more than possible that the dynamicists will say, look, there's no way you can do it. These can't be captured. It's possible that tomorrow Bill Botke will wake up and go, oh, I've come up with the idea. This is how it works. So that, but the remote sensing, non-compositional end of things also has an important role to play, and I'm not the one to say it.
Well, you do a good Botke, but it's a little slow.
We lived together for years.
So, Mike and I, there's been some conversation here about concerning MAVEN with the idea that possibly understanding the space weathering environment. And again, I'm not sure whether MAVEN's payload is suited for that, but I think we have a comment down here from Rachel about the possibility that the relationship that you might be able to learn something about the space weathering processes from MAVEN. Do you have any thoughts on that? I'm clueless myself.
Yeah, I don't know. I don't know whether I can imagine arguments in both directions. I can imagine some argument that, look, we know what the UV coming off the sun is. We know the distance to Mars, so it's just going to be whatever, an R squared sort of thing. I don't know really anything about exospheres. I don't know if there's enough. I don't know how the environment of Mars would, or the presence of Mars would affect the solar wind around it. I don't know if Phobos goes through some sort of magnetotail or some place that's just blocked. It seems like the Mars facing side of Phobos would be a lot less exposed potentially to space than the anti-Mars side, just because Mars is so big in its sky. But I'm continuing the hand wave. It's
Okay, here's another one. Richard Jarosek pointed out that you were talking about the possibility of hydrated minerals at depth. Would we expect any spectral significance from recent impacts, say, that might reveal some of that? Has anybody seen any even hints at that?
If I don't think we have the spatial resolution with the Chrism or the Omega data to really rule that out. If I mean the hydrated minerals, we know that hydrated minerals survive on the surface of asteroids because we see it on plenty of asteroids. They survive in meteorites coming to the ground. So if the surface of Phobos and Deimos has been desiccated, there would be the question of whether it's. So we see a little bit of OH on their surface. We don't see nearly as strong a band as we see on many asteroids. Whether that's because the whole body got heated, whether it's because the very surface is extra mature in a way that you get at 1.5 AU and you don't get at 3 AU. I don't know, but I think that ties into the suggestion. I think that was Dries who said that maybe you'd want an impactor to get fresher material. Certainly, if we had a Phobos mission that did absolutely everything we wanted, we would want to get below that surface, and we would want to see at depth and see how it changes, and see if the very surface is different from down a few centimeters or more.
Okay, Andy, that's pretty much the end of the questions we've got here, and I want to really thank you for an excellent presentation and really good graphics and a very systematic treatment of these issues. And it's been extremely helpful from our point of view. And so I think you've also quite nicely made it brief enough so that we could all get home to our Canadian Thanksgiving dinner of moose with beaver stuffing. So
poutine, it's got to be poutine, right?
So thank you very much, and we look forward to next week when Sasha Basilewski will talk to us about the geology of Phobos and Deimos. Thank you.
Thank you all.